Okay, we are ready for the lecture now.
Yes, so I'm happy to see you again. And we'll continue our work on word maps and linear algebraic groups. And I want to remind you the main achievements of our first lecture. So, uh, first of all, it's the main theme, so to speak. My goal is to build a sort of a bridge between equations in semi-simple algebraic groups on the one side of the bridge and between equations in matrix algebras on the other side. Here the expression in equations in matrix algebra is not so well defined because well, normally I mean here associative algebra, as most of people thinking about matrix algebras, but as a first step, it is easier for me to consider, uh, sorry for stupid expression, the third side of the bridge. Bridge has only two sides, but here I need another one, auxiliary side if you wish. I want to consider equations in Lie algebras. In our case, in semi-simple Lie algebras. Or to make life easier, we restrict our attention to simple algebraic groups and simple Lie algebras. Once again, you may think as a toy model, but a very good one, SL group or algebra, associative algebra or Lie algebra. So I'm considering matrices with determinant 1 if I want to focus on group structure, or if I want to consider associative or Lie operation, I um, consider trace zero matrices. And today I'll speak about Lie algebras in the first part of today's lecture. So our operation is Lie bracket xy minus yx, which I traditionally will denote by square brackets. Okay. So our main achievement, not really ours, but Armand Boreless, he proved the main theorem saying that if K is any field, G is a connected semi-simple algebraic group over K, and W is a non-trivial word, then the corresponding word map is dominant. And sorry, I'll remind you what this means. This means that the image of the map, which corresponds to our word, contains the risky dense open set. So informally, for typical right-hand side, whatever this means, the word equation is solvable. So it's the main conceptual result in the theory of word maps. And now uh, we want to consider uh, a counterpart of this theory on the third side of the bridge, so for Lie algebras. So we are going towards getting sort of infinitesimal analog, and we want to compare two situations: what's going on for our algebraic group G with what's going on with its Lie algebra German G. And as I showed you as a sort of a trailer at the end of our first lecture, this situation looks uh, uh, as follows. Informally, usually looks well. Usually, it's much easier to work with Lie algebras comparing with your original object algebraic group. It's typical for mathematics. Uh, our algebraic group G is a nonlinear object, in spite of the fact that it's called linear algebraic groups, but it's something highly nonlinear. And on the contrary, its Lie algebra is, after all, a vector space, so something which belongs to the universe of linear algebra with a sort of operation, which is also nice. So usually the picture on the left-hand side of this slide corresponds to the situation. On the other hand, in the opposite direction, say going back from Lie algebras to algebraic groups may be very tricky. And the illustration is on the right-hand side of the slide, mountain road in Himalayas, so it's how it looks like. But let's see what's going on in our case. See, let's try a straightforwardly optimistic transfer. So what I mean is that we considering any field K, any connected semi-simple algebraic group over K, it's Lie algebra, German G, and instead of considering words, we are considering something analogous for Lie algebra. So we are considering what's called Lie polynomial, and here I'm restricting myself by looking at monomials. So what I don't want to go into formal definitions. So what's Lie monomial? So for instance, you consider a commutator in our group, say x comma y, which in the sense of groups means xy, x minus 1, y minus 1. And you attach to this expression the same, so to speak, expression x comma y in brackets, which corresponds to the Lie operation. That's what I call Lie monomial. So you can, of course, consider iterated commutators, more complicated expressions. And if you do not want to restrict your attention to monomials, you want polynomials, just consider, just add two additional linear operations, say multiplication by scalar and addition. That's how you get Lie polynomials. What do I mean by Lie polynomials? I want to emphasize that you have to take into account the laws which are satisfied in any Lie algebras. Anti-commutativity, x comma y equals minus y comma x, and the Jacobi identity. So if you have, say, a polynomial x comma y plus y comma x, it is identically zero. That's what I. And we would want to say that the corresponding map is dominant, as in the case of algebraic groups, but this statement is wrong. It's totally wrong, I can say. Why? Well, to convince you, let me show you an explicit current example, which is very counter-optimistic, because, well, the polynomial is, after all, not so complicated. You see, say, you consider the bracket of, well, two brackets. Each of those contains 5 terms. And our Lie algebra here is just SL2. So trace 0, 2 by 2 matrices, extremely simple, the most simple algebra you can imagine. And surprisingly, this polynomial takes only zero values. It was discovered by Yuri Razmyslov in 70s. I told you about that um, last time. Razmyslov and independently Furmanek discovered many interesting uh, polynomials, say associative but non-commutative. Uh, it's another story, and I don't want to go into details, but they were first to disprove some common expectations and to construct explicit polynomials on matrix algebras that take only central values, so only scalar diagonal matrices, which was sort of big surprise that time. They are more complicated than this example, but once again, not very complicated after you discover them. To discover them was a sort of a challenge. You see, we are stuck here. So we cannot speak about such highway at all because we see a polynomial which takes only zero values, so no hope for dominance. But after, say, cooling down, we can, take some more sober view on this situation, which could be illustrated as follows. Okay, it's not a highway because this road contains a sort of potholes. And if we localize potholes and if we put a sort of a fence that would signal us drivers about these obstructions, maybe we can arrange the situation and continue our movement on the way to infinitesimal analogs of Boreless theorem. And indeed, it turns out that this is possible. Let me tell this story. And before stating results, let me state a refined question. So we have to assume something. So we are looking at some Lie polynomial, which is formally speaking an element of the finitely generated free Lie algebra over an algebraically closed field K. We fix some semi-simple Lie algebra G over K, and we consider the corresponding polynomial map. I do not call it word map because it's now not word but polynomial, but it's the same principle. It's evaluation map. So instead of capital X1 and so on, capital XD, I substitute elements of our Lie algebra G. Then I perform all operations which appear in the definition of polynomial. Say I compute all Lie brackets. I perform all multiplication by scalars and all additions. And as a result, I obtain some element of our original Lie algebra G. So it's well-defined map. Of course, it's not a homomorphism of Lie algebras. The same situation was for groups. It was the word map. Let me remind this, that it is by no means a group homomorphism. So here our P also is not a Lie algebra homomorphism. And we ask something about this map. Once again, is it dominant in the same sense as for groups? But here we impose an additional condition, which is necessary, as we saw, that this polynomial is not identically zero on our Lie algebra G. This is a question which we want to investigate, and to tell you the truth, the answer is still unknown in general. we cannot prove this in full generality, and we cannot provide any counterexample. So the situation in general is wide open. So frankly, we do not have a precise analog of Boreless theorem, even under this natural and necessary additional requirement that polynomial is not identically zero. But the situation is not as hopeless, and I'll say something positive in a minute. Meanwhile, if you have a question or remark, maybe it's worth asking. Well, if not, I'm continuing. Sorry, I didn't hear the question.
Uh, can you say what is free D algebra?
Freely algebra, yeah,
Again, and
I
just
don't want to go into definitions. Say
yeah,
you can
just
say
explanation.
you have to think about something like full free group. What is free group? You consider a collection of words in some alphabet. To
Yes,
be on the safe side, let's consider finite alphabet. And
right.
a free group is a collection of words where you consider expressions like monomials containing these x1, xd, and also the inverse elements. What about freely algebra? The same principle. You start with d variables x1 and so on xd, yeah, and you allow yourself expressions which appear after you applying Lie algebra operations, taking Lie brackets of any of x1, xd, uh, multiplication by scalars, elements of k, and addition in k. Yeah? And
Right.
uh, you take into account that these expressions satisfy only uh, the laws which hold in any Lie algebra. So anti-commutativity, so x comma y equals minus y comma x, and the Jacobi identity. Yeah, so
Right.
no other relation. Yeah, the same principle as in groups. Now in chat,
Groups.
some
Yes. Right.
asked me about dominance. What's the uh, what about dominance? So yeah, it's the same principle. Lie algebra is a vector space. So vector space is an algebraic variety of a K, and the same definition, the map of algebraic varieties, vector space is a particular case of algebraic variety, is dominant by definition if it contains a dense open subset. So absolutely the same definition. Well, so what can we say about the answer to this refined question? We have a theorem. I say the main theorem, which we proved well about 10 years ago in our joint work with Tatiana Bagman, Nikolai Gordeev, and Eugene Plotkin, which says the following. So I'll try to explain the statement of this theorem. Here we see that our L is a Chevalier algebra. L, which depends on our field K, of course, and on R, where R is a root system, reduced root system. So what is a Chevalier algebra? In other words, I could say that it's a split Lie algebra. I'll explain you more later today when we'll speak about Lie algebras which are not split, which are not Chevrolet. So roughly, what does it mean? I consider the Lie algebra of a split semi-simple algebraic group. So you can think about the same toy model, Lie algebra SL of trace zero square matrices, which is the Lie algebra of the algebraic group SL, square matrices with determinant 1. Well, we proved it for any characteristic, and the only problematic case is characteristic 2, as often happens. We have to exclude some bad cases here, but let me leave this aside. I want to show you some streamline and not technicalities. So forget about small characteristics. Think about characteristic 0 to be on the safe side, and in that case, no restrictions at all. So you consider something like SL or a split simple Lie algebra of any other type, A, B, C, D, E, F, G, as usual, according to the Killing-Cartan classification. By the way, I can say that historically, these objects appeared before linear algebraic groups in a sense, because Killing and Cartan worked with Lie algebras rather than with algebraic groups. Of course, for them, the motivation was in Lie groups, but not in the theory of algebraic groups. Algebraic groups historically were studied later by Chevrolet and then by Boreless and others. So it's a sort of a primary object, the object of primary interest for algebraists, split Lie algebras. So for these algebras, we can show the following. Now we consider a polynomial which is not an identity of the Lie algebra SL2. I bring your attention and want to emphasize that it does not vanish identically on SL2, not on L, but on SL2. And under this assumption, we can prove that the induced map is dominant. So it's a sort of best approximation to Boreless theorem in this universe of Lie algebras. Let me say something about this statement. What's the meaning of the assumption made here? So this means, if we come back to our first lecture, if you remember, the main line of the proof of Boreless theorem, I intentionally spent, I think, half an hour to show you a sketch of the proof, which was detailed enough. And there, I brought your attention to the induction base. In the group case, we started with the group SL2, and the first step, which was essential and not at all obvious, we used Tit's alternative or Platonov's theorem to show that there are no group words which are identically one on the group SL2. This was our starting point, and this starting point allowed us to proceed by induction. Here, Razmyslov showed us that there is no hope to proceed along the same lines because the initial step breaks down. We have no analog of Tit's alternative. We have no analog of Platonov's theorem. Platonov's theorem, I remind you, said that there are no non-trivial laws in simple algebraic groups, but Razmyslov discovered a law in simple Lie algebra. So the first step breaks down, but if we assume that our polynomial is good enough, not of Razmyslov type, under this assumption, we can proceed by induction, more or less along the same lines. And let me formulate a version of this theorem, which is, well, maybe even more useful practically. So we ask whether there is a way out if P is identically 0 on SL2, say for Razmyslov's polynomials, and the answer is yes. What I want to say that we also proved in the same paper the following fact, that under the same assumptions for Chevalier algebras, let's suppose that our polynomial is dominant in two cases, for SL3 and for SO5. I denoted this for A2 and B2. The case of root system A2 is the Lie algebra SL3, and B2 is the orthogonal Lie algebra SO5. Lie algebras of rank 2. Then P is dominant for every simple Lie algebra. So what's the way of proving this theorem? I omitted the proof. I'll prove something. My principle is that in each lecture it's worth trying to prove something, but there are other things I would like to show you with proofs or with sketches of proofs. So I omit the proof of this theorem. The interested persons can look at our paper. I'll explain the idea in a few words. So we tried to mimic Borel's proof. In what sense? Okay, we cannot do anything with the SL2 case with induction base. So we assume that for our polynomial, the induction base holds. And here induction base is restricted enough. A2 and B2, we do not even need G2 for the same reasons as in the group case. G2 contains A2, they are the same rank, and we can mimic the group theoretic argument in the Lie algebraic setup. And the main story is around the induction step. And the induction step in the group case, there were several options, and one of them was based on the Deligne-Sullivan trick. And the Deligne-Sullivan trick works here as well in the universe of Lie algebras. Also, another thing which is to be modified, if you remember, we used in an essential way the fact that the image of any word map is invariant under conjugation. A similar principle holds in the case of Lie algebras, because here the image of a Lie polynomial is invariant with respect to the so-called adjoint action of the corresponding algebraic group. So in simple words, we replace conjugacy classes, which were essential for us in the group case, with orbits of this adjoint action in the Lie algebraic case. And we modify Borel's proof, well, so to speak, mutatis mutandis, And this works. The induction step works. So essentially, we repeat Borel's proof, omitting the induction base, which we replace by very restrictive assumption, and we mimic the induction step doing appropriate changes. So not a big deal after all. So that's what we can do. And unfortunately, we cannot do anything else. We cannot do better. For instance, just for those who like challenging questions, I didn't write down it, but even in the case A2, so SL3, we do not know whether we can drop this assumption that the map is dominant. For instance, let's suppose that our P is identically 0 on SL2, yeah? So the necessary condition. Can we say that it's good enough in the following sense? We don't know whether there exist or not polynomials, Lie polynomials, that take all values on SL3 with values with diagonal matrices. Such map would not be dominant, of course, and would immediately give a counterexample to Borel's theorem. Why should we be careful? Because I told you that in the third universe, which is interesting for us, in the universe of associative algebras, such polynomials do exist. These are for Manik-Razmyslov central polynomials that take all their values inside the collection of the diagonal matrices. But they are not Lie polynomials. They are associative non-commutative polynomials, but not Lie polynomials. So once again, we do not know whether there exists a Lie polynomial on SL3 taking all its values inside the collection of diagonal matrices. It's tantalizing question. We spent a lot of time, of course, also with computer experiments, with all sorts of theoretical attempts, but we totally failed. No counterexamples and no proof. We produced several wrong proofs and we discovered gaps ourselves, but we were not able to produce anything correct. So one of the goals of my mini course to bring to your attention several simple looking, maybe deceptively simple looking, deceptively simple-minded question, which may be difficult. So let's about dominance on Lie algebras. That's what we can say in parallel to Borel's theorem. And now something else. How about going from dominance to surjectivity? I remind you that in the group case, there were not real gaps between these two notions. At least there are not known examples, except for power maps I mentioned in the Chatterjee-Steinberg theorem from the first lecture, where there is such a gap. All non-trivial maps are dominant, but only power maps may be non-surjective. That's V. So what about Lie algebras? What's going on here? And okay, we saw some pathological examples due to Razmyslov that the map is identically zeros, but it's not dominant and not surjective. It's not something which reveals some gap between dominance and surjectivity. So this is a meaningful question, whether there are examples of such maps. And it turns out that in this universe of Lie algebras, one can find such examples, which also was for us a sort of surprise. Here is an explicit example. Let's consider the following monomial, yeah? xy comma x and comma with xy comma y. Very simple expression. And we are looking at this expression on the SL2. So what's going on here? I want to show you proof of the statement that it's dominant but not surjective. First of all, the dominance follows from our theorem because it's not identically zero. Why it's not surjective? Here is a computation. We use the standard basis of SL2, E, F, and H. Physicists would call it Dirac basis or Pauli basis. I'm not an expert in quantum mechanics. They always use this notation. Well, for us, H is a semi-simple element, and E and F are upper diagonal and lower diagonal matrices. So what's called the standard basis. And one can show that the image of the polynomial map corresponding to P contains no elements, so nilpotent elements of special form, ME or MF. So coordinate axes corresponding to the elements E and F are excluded from the image. And here is the computation. I give a hint and I suggest you to fill all the details. First, we note that the value of our polynomial does not change if we modify the first or the second argument as shown here. This allows us to assume that to exclude one of the, to make one of the coefficients zero in the expressions for x and y, and then just substitute, we give such an expression, and just looking at this expression, you show by the way of contradiction that no elements of the form ME or MF can belong to the image of this P of xy. So a very explicit construction which shows that this polynomial map on the Lie algebra SL2 is dominant but not surjective. And to be even less optimistic, I'll convince you that if we go back to algebraic groups with the hope to get a counterexample which would show a gap between dominance and surjectivity in the group case, we fail again. So I mean that here we are again going along this mountain road because this phenomenon disappears in the group case. Tatiana Madman made magma computations that show that she showed that the corresponding map in the group case, so in the group SL2. So here I emphasize the difference between the two cases by changing capital X and Y to small x and y. Small letters correspond to the group case. So here our map is surjective on SL2. That's the picture. So not too optimistic, but several good questions to work on them. Just let me prevent you from being maybe over optimistic that these questions seem not easy. Well, maybe it's also a good point to give you an opportunity to ask questions. No questions so far. Well, let's go ahead. So I hope I convinced you in showing difficulties here. Now, something positive that we can say. Well, for particularly polynomials, we can say something positive, and even more than in the group case, which shows that our model of highway as a road from groups to Lie algebras was not so wrong. Say for angle polynomials, one can show that the corresponding maps are always surjective. Well, over sufficiently large fields, some finite fields should be excluded, and also some small characteristics should be excluded, but in general, this is okay. In particular, somebody asked me a week ago, what about commutator? Commutators are also good enough, but for simple Chevalier algebras. And here we have another problem. So let's consider real Lie algebras, simple ones. And let's restrict our attention to the simplest angle, to single Lie bracket, commutator, x comma y. Even here the situation is unclear. So it is known that each element of L is a single Lie bracket, but this is known only in two extreme cases. L is split, so what I call Chevalier algebra, and another extreme case that L is compact. Say the Lie algebra of compact form of a real group. What goes on in between is almost completely open. There is one paper by Dmitry Afiezer, recent enough. He proved that this bracket map, commutator map, indeed is surjective, but in general, the surjectivity problem is still wide open, even for this simplest case. No counterexamples, no proof. So if there are many Lie algebras over reals which are neither split nor compact, something intermediate, they have a real rank, positive real rank, at least one, but they are not split, not maximal rank. So they have a Cartan subgroup of intermediate rank. Nothing can be said so far for this simple situation. In fact, I tried to take care of this case, speaking with real algebraic geometers, because after all, when you translate the problem into the language of equations, well, x comma y, just substitute entries of matrices and multiply, you'll get some quadric, and you will get some intersections of several real quadrics, and you have to decide whether such a real algebraic variety has a real point. The problem of real algebraic geometry, but experts in real algebraic geometry told me that such problems are in general hopeless so far. So each particular case, you can apply some trick, but in general, there is no algorithm. They cannot prove that the problem is algorithmically unsolvable, of course. But there is no practical algorithm to prove or disprove the existence of a real point on a given real algebraic variety. So, once again, for those who love challenging problems and maybe who are good enough with computers, I could say that going over case by case and the Dinkin classification, or the Killing-Cartan classification, one can treat case by case all possible situations with the help of computer, but this is a piece of work. Oh. Well, what else? I think that that's all that I can say about the case of Lie algebras. Maybe I'll just repeat what I said answering the questions a week ago, that if you allow yourself infinite dimensional simple Lie algebras, the situation is totally different, of course. However, explicit counterexamples to the non-surjectivity of the commutator map were not known until recently. I think that the first counterexample was constructed in our preprint, which is on archive recently and joined with Adrien Duboulot and Andre Regueta for Lie algebras of vector fields on some algebraic curves of higher rank, of higher genus, sorry. But in general, well, the situation is totally unknown for Kac-Moody Lie algebras and for other simple Lie algebras. So there are many interesting things to do there in the infinite dimensional setup. But we are going back to simple algebraic groups. Well, I told you last week that Boreless theorem is essentially the only known general fact about word maps. General, I mean in full generality. But if we cannot say more in general, we will try to say something in some special cases. Special cases may mean several different things. We can specialize words. This will also be discussed. And we can specialize groups. This will also be discussed, especially SL2 case. This will be the topic of our next lecture in a week. But also, we will restrict our attention today to two cases where the field is fixed. Today we'll, in the second part of our lecture, we will consider a complex field a little bit. Once again, I postpone some discussions to the third lecture, where we'll take care of SL2C. Today we'll focus on a real field, and I'll say something about non-Archimedean analogs as well, because I told you that I like number theory. That's why whenever possible, I will say a few words about something more arithmetic. Well, so we have Boreless theorem, which settles dominance here, but we'll talk about the surjectivity and eventual gaps between the two. So what are the main questions here? So I repeat that we start with a connected semi-simple algebraic group over K. By Roman G, we consider the group of points. You know, when our field is not algebraically closed, we have to be careful. So we have to distinguish between the group of points and the group scheme over real estate. Now W will denote a word, and if unless stated otherwise, I assume that it is not a power word. So W is not a proper power of another word. If it is, we mentioned the theorem by Chatterjee and Steinberg, which provides some pathologies, some examples to surjectivity. So we assume that W is not a power word. And here are my main questions. The first one, I remind you that it's reasonable to consider only groups of a joint type because I started my first lecture with examples for power maps. And in the real case, I will consider split groups of a joint type and also compact groups. So 3 setups, and we ask the same question. We want to know whether or not the word map induced by the word W is surjective. So in the first 2 cases, 1 and 1 prime, the question is open in each of the versions, even in the simplest cases. Say PSL to C, PSL to R, even for words in 2 letters. So in general, nothing is known. There are many facts, there are many attempts, there are many approaches. The case PSL to C, as I told you, will be discussed in a week. The real case will be discussed today. Something is known here, but no complete answer so far. I remind once again that was already told that naive attempts to use Lie theory fail, even in the cases where the exponential map is surjective. Yeah, say we saw earlier examples where the Lie polynomial induces a surjective map, whereas the same word, where each Lie bracket is replaced with the group commutator, may induce a surjective map. Say Lie polynomial may not be surjective, but the word map will be surjective. So why, informally, why do we see such a phenomenon? It's a little bit strange at a glance because, well, in Lie theory, we know that this should work. And the point is that informally, somebody told me that the whole point is in the fact that the group commutator and the Lie bracket are different things. If you work with simple Lie groups and simple Lie algebras, the correspondence may work well if you are in the setup of nilpotent Lie groups, nilpotent Lie algebras. Some of you may know the situation where the Campbell-Baker-Hausdorff gives you a nice correspondence, so you have a very nice maps, exponential map and logarithm map. But in general, as we are convinced by looking at our current examples, there is no good bridge. We have to think much more to build new bridges between the 2 universes. So let me make something more modest and to consider now the compact case where the situation is better. So what do I mean? In compact case, we have some results, and most of known results may be called negative positive. In one sense, uh, you see, we consider uh, a particular word W and a particular group G, but we can vary this or that. And if we fix a group and change the words, then we can eventually arrive at something negative. So fixing a group, we can find a very bad word such that the corresponding word map, will be not surjective and very far from being surjective. And positive results can be obtained in the opposite manner. We fix a word, even a bad one we found, and we are starting to enlarge our groups, and eventually we can hope to get a surjective word map. So this is a typical situation in a sense, and I'll show you two theorems in these directions. So we consider here what's formally called anisotropic forms of simple algebraic groups over the real field. So connected, compact, simple Lie groups in another language. The first theorem. So let's consider such a G over reals. Consider the group of real points. Then in certain metric on G, we can say the following, that for any epsilon, there is a word in two letters such that all its values fall in the epsilon neighborhood of the unit element of the group. That's what was mentioned during our first lecture, Tom's theorem, when I talked to you about so-called Panda Principle, what is typical, what is not typical. So it's the negative results. We fix G and vary W. And varying W, we can arrive eventually to some very bad, very far from surjective. On the other hand, the second theorem, which is due to Hui, Larson, Shalev, says something positive, some almost surjectivity in a sense. That let's fix two words in disjoint sets of variables, W1, W2, and let's consider the product of these words. So we composed word map, and then for sufficiently large group, this word map will be surjective. So in a sense, this means that for any W, you will get word with at most two of our group G, which is sufficiently large. There is a more optimistic conjecture due to Michael Larson, which I'll discuss later, but still the second statement is a sort of positive results. Fixing a word, we can enlarge G so that to get something very close to surjectivity. These are difficult theorems. I will omit proofs. Certainly, I will give both if our course were longer, but for such short 4-lecture course, I had to compromise, and I omit the proofs. Of course, you can look at the original papers. You can look at our survey paper with Gurdjieff and Plotkin. In Russian mathematical surveys, we present some modified proofs of these results. Anyway, they are very far from straightforward and tricky enough. Instead, I'll give you a PDIC analog of the first statement, which is in a sense simpler for those who know a little bit about periodic numbers. This will be done a little later. And as to proofs, I want to consider the case of simple real groups, and there I will prove something a little bit sketchy, but almost in a complete way. Well, some more comments on this. So first of all, as I told you, the first statement is a theorem of Andreas Thom. In fact, he considers some more special case, which is not far from general one, a unitary group, word into letters, and the metric which is induced by the operator norm on the unitary group. In fact, one can easily go over from any compact group to a unitary one using faithful continuous representations and restricting your metric to the image. And also, instead of the operator norm, it's, to my taste, somewhat easier to consider, well, the Frobenius norm. In fact, what we need is some invariant norm. This means that this does not change after multiplying on the left and on the right by unitary matrices. Frobenius norm is just usual square root of sum of squares. This version of the proof is contained in our survey. Essentially, it's the proof due to Thom, nothing more than that, but some little modifications. And as I told you, the second statement is a theorem of Huy-Larsen-Scheref, a little bit more recent. And this is a step towards the conjecture of Larsen, as I told you. It's already a long-standing conjecture, say 13 years, no progress so far, that asserts that any word map is surjective if you enlarge your group from the point of view that you make its rank bigger, as big as you wish. And a little bit weaker form of this conjecture was proved by El-Kasapi and Thom, as I mentioned their work in our first lecture. So that's the situation for compact groups. It's much better, as I told you, and also there are several remarks to be said here. First of all, we can observe the same phenomenon over non-Archimedean local fields. Say, think about periodic. If you consider anisotropic simple groups over periodics, these are necessarily of type AN. It's a general fact in algebraic groups. You cannot get anything anisotropic for B, C, D, E, F, G. And Breuillet's theorem, with some modification by Rousseau, says that it is anisotropic if and only if its group of points is compact in the natural topology, so to speak, induced by the evaluation of QP. Now, say a sketch of the proof of Thom's phenomenon. So I told you that our G is of type AN, so practically this means explicitly that it is the group of elements of norm 1 of some division algebra D. And moreover, we have some fine structure on this group, sort of filtration with normal subgroups. Here it is. For details, I send you to see. There are many places where you can find this. To my taste, the best exposition is in the textbook by Platonov and Rapinchuk, Algebraic Groups and Number Theory. You can find this filtration. And the point is that if you take your word lying sufficiently deep, then you will observe the phenomenon discovered by Tom. Let me make this more precise. So we have this norm, p-adic norm, which is induced by p-adic valuation. Once again, I do it quickly because I'm not sure that all people here are aware about details of non-Archimedean analysis, but just to give you a certain flavor of things here. So this norm is invariant with respect to multiplication. And now take W deep enough. So I consider the filtration on our free group. So if informally, if our W is an iterated commutator of sufficiently long iterated commutator, then we have the inequality which is written here. So this is an exact analog of Thom's phenomenon. So for any group, here SL1D is an arbitrary compact group in the p-adic case, and for any such groups, it admits a word which behaves as bad as in the real situation discovered by Tom. Absolutely the same phenomenon. And the final remark here, that in a recent preprint, Gurdjieff extended this notion to not necessarily algebraic groups. He defined the corresponding notion in the case of arbitrary compact topological groups, and under appropriate assumption, he proved that Thom's phenomenon can always be observed. And also some people reformulated this phenomenon using other terminology. They used the term almost laws. Indeed, we see here a sequence of words whose values are not identically one, but they converge to one in an appropriate topology. And there are, I know, at least two papers where this was investigated. Many Aka, Emmanuel Broyard, Leo Rosenzweig, and de Saxe. They introduced such phenomenon, and also El Kasapi and Tom and another paper, they looked at this phenomenon. So this is an interesting situation, and in the last 20 minutes of today's lecture, I'll discuss non-compact groups. Let me stop for a moment and look. Maybe you have something to ask here. Well, so let me continue. I hope to give here a sketch of a proof of some statements. I do not hear if I hear that somebody wants to ask a question, but do not hear.
Sir, what was Larsen conjecture?
Sorry?
Hello. What was Larsen conjecture? You mentioned it regarding connected compact algebraic groups.
Larsen's conjecture was as follows. So let's fix some with W, yeah, and then there exists some constant C depending on W, such that for any compact, real, simple algebraic group of rank larger than C, the word map induced by W is surjective, 100 points. What they proved together with Hui and Shalev is slightly weaker. So surjectivity means that any element of the group of real points is a single W value. And they proved that any element is a product of two W values. for sufficiently large groups. So you see still there is some gap between width 1 and width 2.
That is for simple algebraic groups?
Yeah, for simple, real, compact algebraic groups, yes.
Okay.
Only for real fields, yes. So real fields, compact algebraic groups, yeah. What's going on for split? I'll tell you now. Okay. Well, so let's consider this situation, and the following question seems the most challenging here. Can one observe here the phenomenon of almost laws? Does there exist a split, say, group? Split, of course, is not compact, such that there are Tom words. Tom words, well, that for every epsilon there exists a word such that the image of the word map falls into the epsilon neighborhood of the unit element. It's open, wide open. Well, to be precise, this is an important remark that if you just consider the group of real points, you may observe some unpleasant situation that it can be non-connected as a group. So you should consider connected component. And it may contain a center. So you should factor out the center to get a simple group. It is known, what's written here is known. Also, you can consult the book of Platonov-Rapinchuk. So we consider the map, the word map on such a group, and we want to say something. Something means that does there exist a non-power word inducing a non-surjective map? Something weaker than Tom's phenomenon, at least one non-surjective map, but as I told you, this is also wide open. What is known? What can be proved? We have the following theorem. You can see the proof for SL2. SL2 is also open, you see. We have the following statement, which is a little bit more general than the original result by Hui, Larsen, and Shalev that is published in the same paper I referred to. So here is the theorem I'm going to prove today. I have 15 minutes for that, and I'll sketch the proof. So let's consider PSL2R, some very well-known group, and this group has lots of interesting properties. Maybe some of you read a book of Serge Lang with the title PSL2R. It appears in mathematics in so many different contexts, so it's maybe the most famous group in mathematics. And we consider any non-trivial word, and we can prove that the image of the word map contains all split semisimple elements. Moreover, if the image of W contains an involution, then it contains all semisimple elements. So what's missing here? Unipotent elements are missing, and also non-split semisimple elements are missing without this assumption. It looks crazy that we cannot prove that the image of W always contains an involution in general. So, once again, a sort of tantalizing problem, and I know many people who worked a lot on this, played with computer. What did they do? They varied W starting from very short words and just case by case arriving at words of sufficiently big length, several dozen letters, still no counterexamples, but no proof. Another challenging problem. So let's prove the theorem. Here the proof is sufficiently elementary. First of all, the case of one letter is obvious. So the power map works in SL2, it's surjective. So we assume that we have at least two letters. And we have two lemmas. One, the first one, not so obvious, I'll prove it. The second one, well known. I'll tell you the general version. Our field is not necessarily a real field. So here there is nothing particular here. Any infinite field, that's why I changed notation. Omega is any word map. Then I claim that there is a polynomial, non-constant polynomial in two variables such that it's 0, this value is 2 at the origin, and for all alpha and beta, the image of the composed map, trace map, and our map, word map, contains all values of this polynomial. So informally, this polynomial covers all possible traces of the elements lying in the image. So it's big enough. The image is big enough. Well, proof of the lemma. It's the idea of Hui, Larson, and Shirley. So two cases. First, let's suppose that there is an n-1 tuple, G2, Gn, which is non-trivial in the sense that the value of our word is not 1. Then we can consider the restricted word. So we take the value of the first variable identically 1. We vary all other letters. It's a non-trivial word, and we can use induction. It's easy case. So we may assume that if we fix G1 equals 1, then the word becomes identically 1 for every G2 and G. What shall we do here? We fix elements G2, Gn, and choose element G1 of some particular form. You see the form, and then the inverse element will be of the similar form, and as a result, you can try to check this manually, that the trace of the value of our omega is a polynomial in two variables. Now we want to prove that it is non-constant. How do we do this? So first of all, if it is a constant, so we use the way of contradiction. Assume it is a constant. Then what's the value of this constant? I claim that this is 2, because if we substitute 0, we get the trace of unit matrix, which is 2. Why unit matrix? Just look. Substitute x equals 0 and y equals 0. Yeah, we have 1 and 1. So we have trace equals to 2. Why this leads us to contradiction? Because here something non-trivial is hidden. The next sentence is highly non-trivial. That every non-central element of SL2 is conjugate to an element of this form. It's a difficult fact proved by Erich Ehlers and Nikolai Gurdjieff in their seminal work on Ores conjecture. It uses some very advanced linear algebra, the so-called prescribed Gauss decomposition. We teach Gauss decomposition in our elementary linear algebra course for first year when we talk about Gauss elimination in a sense, but there are subtler versions of Gauss decomposition which are due to these two guys. Okay, so let's trust them and believe that this statement is true. Then we have trace 2 for every n tuple, yeah, where G1 is of the form written above. So this means that as soon as we have trace 2 for the element of the above form, by this Ehlers-Gurdjieff theorem, trace is invariant under conjugation. Values of W are also invariant under conjugation. We have trace 2 for every n tuple. And this is in a contradiction with Borel theorem, because when do we have trace 2? When the matrix is unipotent. We are in SL2. And the image cannot contain only unipotent elements, because in this case it would not be the risky dense. So this would be in a contradiction with the Borel theorem. So it is a non-constant, and that's the proof of the lemma. Yeah, first lemma is proved. The second lemma is very easy. If we have a semi-simple element, then it is split if and only if its trace absolute value is bigger than 2, and it is of order 4 if and only if the trace is 0. It's well known, but let me sketch a proof. Then if we have such an element, it is either in split torus, semi-simple element, and it is of this diagonal form, or it belongs to a compact torus, anisotropic torus. So it's a rotation. Yeah, it's what we usually call a rotation when we teach linear algebra. So it's conjugate to such a matrix. There are two cases, and in the first case, we have the trace is at least 2. In the second case, it's at most 2. It's an elementary observation. And moreover, when can we get 0? When cosine is 0. And in this case, sine is 1. So it's 0, 1 minus 1, 0. It's an element of order 4. So they prove the second lemma. How do we finish the proof? We consider our word map. Now, as in the proof of the first lemma, we may assume that it is identically 1 for every G2, GD. Otherwise, we can use induction. Now, as in this lemma, we consider the non-constant polynomial. But you see, now we use something special. It is a real polynomial. So it's a function which is continuous in Euclidean topology. It's also elementary real calculus. That's what we teach our students, yeah? So what's the value of such a polynomial? Either all real x's or real numbers, say semi-infinite interval, starting from r to infinity or from r to minus infinity. Yeah, that's the only possible options for the values of a real polynomial. And well, now 2 is the trace of this polynomial at the origin. So this means that either all elements have trace at most 0 or at least 0. Yeah, but you see, we are in PSL, not in SL. So in all cases, PSL means that we can multiply by minus identity. So we can get either trace of G is at least 2 or trace of minus G is at least 2. So every split semi-simple element belongs to the image. So here is the proof. But once again, only split semi-simple elements are covered with this proof for SL2 only. For SLN, I don't know what's going on. And well, here is the argument about order 2. It's equivalent to the existence of an element of order 2 for PSL because of this -1, -1. And we finish the proof according to the two lemmas, because either the traces are all negative or all positive, and multiplying by -1, we get everything. All semi-simple elements are covered here. To finish, I have a couple of minutes. Well, what are our expectations? In fact, no expectations here are well-grounded, so no background, no sufficient evidence for any expectations, but, well, suppose that we will find some gap between dominance and surjectivity, some word maps which induce non-surjective maps over reals or over complex numbers. An interesting question is whether this can be detected over R. Let me make this more precise. What's the question? So we consider, once again, connected simple linear algebraic group or joint type. Consider the identity component. We consider non-power words and assume that the real map is surjective. Can it happen that the complex map will not be surjective? So, is such a situation possible? No answer so far, but to convince you that this is a meaningful question, let me make the last remark. If we consider power words, such a situation can happen. Once again, I remind you the Chatterjee-Steinberg theorem. Consider squaring map, consider compact form of a simple group of orthogonal or symplectic type, and then the squaring map is surjective on the real form, but not on the complex group. So the question is, can we observe such a phenomenon in the non-power situation? Once again, the question doesn't seem easy. Let me stop here. Today I'm not out of time. We have several minutes for questions, remarks, comments, so please go ahead.
Thank you.
Thank you for your attention. So
Anyone
next
has
time,
any question?
yeah, yes, please. Next time I'll discuss SL2C.
Okay.
This simply looking situation, but once again, perhaps this is the problem I devoted so much time, maybe comparing with any other problem during my career, but totally failed. And there are several particular results and several approaches, and maybe some sources of some ideas can be used in other situations as well, but still the problem remains as open as it was. Anyway, I would like to use this audience consisting mostly of young people to give them, well, some hints if somebody will be interested. And maybe I'll tell something else. But so far for today, it's everything I wanted to say. Thank you for your attention once again. And also, if you want me to discuss something particular, please write me. I'll try to answer questions.
Sure.
Bye for now. See you next week.
Okay.